Okay, off we go. So before we get into the math, super quick reminder, don't forget about the attendance code, attendance quiz, blah, blah, blah. Second of all, how about full props for Duke Facilities getting the AC fixed before class started? That's totally awesome. So anyway, much appreciated. Okay, so moving along. So we were talking about the chain rule, and let's see here. Last time we talked about a warning. Don't confuse variables. It's an easy sort of unforced error, really. Confusion of variables. There's no reason for it. Just change variables as needed and make sure you're composing functions with the variables named accordingly, right? Is kind of the short punchline. So that's a special case of a more general problem, right? So what we're accustomed to doing at this point is so we're composing functions, but you write the variables out, and which variables depend on which other variables in a diagram, and using the diagram and just writing down the formula for a partial derivative of a composition, using the diagram and intermediate variables. So there is a point of view that sort of moves away from thinking of it as a composition of vector value multivariable functions and toward a game that you play on diagrams. Now, here's the problem. Not every diagram comes from a composition of functions, right? And to be clear, our chain rule, here it is, right? This is the only version of a chain rule we've actually demonstrated, right? And this is specifically and only, right, when you're talking about a composition of functions. And when you're composing functions, what comes out of the first function has to be exactly what goes in to the second function, right? And furthermore, we need this to be a free domain. We need all these variables to be sort of unrelated. I can't have y1 being a function of y2. That's not what we're talking about. That's not how functions work. Okay. So, with that in mind, let's look back at, here we go. Oh, why am I not in full screen mode? There we go. We look back at this diagram here. This is not. It just isn't, right? If this were a composition of functions, what is Z1 a function of? And I guess we would have to say it's a function of these three variables, because each one of them, as the diagram indicates, directly affects values of Z1. That's just not what the diagram on the left looks like, right? And so why do we care? Okay, well, first of all, we don't technically have a theorem that addresses this. Second of all, I don't even know what this means. If you really want to get right down to it. So in particular, if I were to ask, what does it mean if I take the partial of Z1 with respect to X1? Okay, so I guess X1's my variable. That means I've got to hold all of the other inputs to Z1 constant. Hey, wait a second. How can I hold Y1 constant if it's a function of X1, which is not a constant? Right? This is a problem. We have a serious problem here. Okay, so now yes, there are ways that you can look at this, and you can kind of reinterpret what we mean by the chain rule, et cetera, et cetera. But I'd like to give you all a way to approach scenarios like this, which in fact just rewrites it properly in terms of a chain rule that we already have, and where we don't have to do hand waving and write down things that we're not clear what they mean. Okay, so here's what I like to do. By the way, we're going to be looking at this scenario down here in this example, and you'll notice these formulas for the various variables are literally produce this diagram. Right, so you can see in particular, for example, Z1 is given in terms of X1, Y1, and Y2. Right, and likewise for the others, you can just go through that list of formulas, and it produces this diagram. And what are we going to do? Again, this is a bunch of nonsense. Roughly speaking, the idea is introduce a new I'm going to do air quotes variable. Maybe I should do the air quotes on new. But anyway, we're going to introduce a kind of a sort of a new variable that will turn what is not a composition into an actual composition. And pretty easy to do in this case. I mean, you can almost kind of see, we've got the sort of the stages, you might say, and the problem here is that we're kind of jumping over a stage. And so, okay, well, how about this? I'm going to introduce a new variable there, and what that variable is it's going to be literally just x1. It's the value of this new variable. I'm going to call it x1 star. The formula for it is literally x1. So when I insert that, okay, nothing's really changing. If I replace an x1 with an x1 star, but whatever, they're the same thing. I mean, literally that's the formula for x1 star. But it allows me to write everything in a way that so we don't have this problem of it not being a composition. Okay, so I'm going to do that. In particular, this x1 right here, kind of that was causing all the problem. I'm going to rewrite that as x1 star. Let's try to get this all on the screen. Rewrite that as x1 star. And let's see what this diagram turns into. It's really going to be exactly this all over again, just, fixed. Here it is, x1 star. That's my new variable. I'm literally going to make it just x1. So technically it's a function of x1. Okay, and then having done so, and then having rewritten this problem formula, where z1 was a function of these variables. That's weird, right? You're not allowed to do that. Well, it rewrites that now, where z1 is a function of the variables in the previous stage, just like it's supposed to be, right? And all of a sudden this problem has poof disappeared. Right? So go ahead now. If you want to compute, let's see, the question was how to compute partial of z1 with respect to x1. Previously, we didn't even know what that meant. It didn't even make any sense, right? And now, no problem. Partial of z1, there's z1. With respect to x1, there's x1. We have three paths, thus giving us three terms. No problem. Everything's fine. And I'll just point to one little quickie phenomenon that happens. If I can get my thing to resize. There we go. A little quickie observation. Let's think about what is this right here. Well, that's the partial corresponding to that step. That step, of course, is where x1 star and x1, they're the same thing, right? So that is, in fact, just one, as it sort of should be, and it kind of disappears. How we doing? Everybody happy? So this turns a problem that we did not have the tools to address into a problem that's fine and dandy and no issues. Okay, all right, now in practice, you probably won't see this, right? But what you will see is people working with diagrams like this and just kind of writing stuff down. In some sense, they're doing all of this kind of in their head because they know what's going on. They know what all these things mean, right? And they know what they meant when they wrote it down. And so they'll just kind of go straight to this. Worse, and I've always found this to just be oh my gosh, terribly unsatisfying. Since they don't write down the new variable, I wanted to be in pencil mode. They'll write their formula for partial z1 with respect to x1 in terms of, among other things, partial z1 with respect to x1. And in their minds, it's clear that they mean different things by these two identical notations. Right? And maybe it makes sense to them. Sure. And I recognize that they know what they're doing. That's fine. But to the reader, this is very confusing because these mean two different things. Right? So I think until you are thoroughly comfortable that you know what you're doing too, don't do that. Right? Introduce this new variable like I've done here and play by the rules. And then you have this convenient distinction that clearly refers to that partial, and this clearly refers to the composition partial that considers all of the paths. Okay. All right. So anyway, heads up about this kind of thing. Anyway, it is what it is. Okay, so let's talk about second derivatives. It's ultimately just taking derivatives of derivatives. It's ultimately not that big a deal. But there is a key observation that's going to make all the difference. And here it is. How this key observation makes all the difference we'll talk about in a second. So I'm just going to, for the moment, call this an obvious statement that if you have z being some function of x and y, so imagine some big expression involving x's and y's. If you take a partial with respect to x or y, the result will still be a great big expression involving x's and y's. In other words, it will also be a function of x and y. So now, how that's useful, we'll see momentarily. Let's just dive in on taking a second derivative. And real quick, I'm going to say don't look at this just yet. Let's pretend that that's not there. And we will see how useful it is in a couple of seconds. Okay, so the question, we've got z is a function of x and y. And then I wrote here r and theta are the usual polar coordinates. If you remember, my favorite way to think about polar coordinates is that, in fact, x and y are functions of r and theta. So I'm going to literally write that down. X and y are functions of r and theta. And let's see, the question is to compute this second partial of the composition. Right? So by way of the composition, z is a function of r and theta. We can talk about a partial. We can talk about a partial of that partial. That's what I want to compute. We don't currently know how to do that. Okay, so the first thing I'm going to do, this first part really is very straightforward. I'm going to compute the first partial. Z with respect to r. Two paths, two intermediate variables, correspondingly two terms. Yawn, right? That's the chain rule that we've already talked about. No big deal. And then having done that, let's observe that I already know how to compute the partials of x and y with respect to r. Because it's polar coordinates, we explicitly know those formulas. X is r cosine theta. Y is r sine theta. So that we could just literally punch that out, right? And let me also point out we have this alternative notation for partial derivatives, and it's just notation, and I made the observation that at some points it's actually kind of convenient to write it as with subscripts instead of as a faux fraction, right? And that's what I'm going to do here. Okay, so why did we take the first partial with respect to r? Well, we computed the first partial with respect to r because the second partial is just the r partial of that r partial. Cool. Right? Okay. Alrighty. Well, how are we going to deal with this? Well, now here's a couple of observations. First of all, when you're taking a partial with respect to r, keep in mind one of the rules of partials is that all the other variables in that world are constant, and so r is in the same world as theta. So when we say partial with respect to r, we mean theta is a constant. Right? This is a really nice property of the diagram, by the way. The diagram reminds me of that, right? I can see the diagram's helping me to remember what different roles, what different variables are playing. And here's the thing: if theta is a constant, then cosine theta is a constant, and likewise sine theta is a constant, and constants, I can factor out those constants right out of the thing I'm taking the R partial of, and so that simplifies things. So that was a lucky break. By the way, you won't always get that lucky. Oh yeah, question.
This is irrelevant, but it smells kind of bad back here. Could you open it up?
Oh, is there a? Okay, yeah. Sorry. Sure. Let me get it. That's not my fault. Let me get this chair over here. There we go. Okay. Okay, so yes, you won't always get this lucky. If you hadn't gotten lucky, let's just take a quick moment to recognize that taking an R partial, when this factor here is not a constant, you would have a product of two non-constants, right? A product of two functions. How would we take a derivative of a product of two functions? It's product rule, right? No big deal, right? It'd just be one extra step here where we'd have to sort of, expand out the product rule first, and then we'd be looking at individual partials and worrying about how to take them. Okay. All right. Okay, whoops. Let's see here. There we go. All right, so we've gotten it down now to trying to figure out what is the R partial of ZX. Let's come back up where we can see our diagram. R partial of ZX. What does that mean? I mean, ZX is not on my diagram. I have no guide on my diagram. What it kind of looks like, now I'm going to write down something that's nonsense. Let me warn you in advance. The following is nonsense. Let me just go ahead and write this down. Nonsense. It looks like I'm taking a partial of Z with respect to X and then with respect to R. You can see the temptation, right, that this feels like that. Everybody see the allure of writing that? Well, here's why that's nonsense. That suggests Z is a function of a collection of variables including both X and R at the same time. And again, I wait a second, I don't know what that means. These variables are not independent. I'm quite concerned about the fact that I don't know how to make sense out of holding all of them constant except for one. Right? So I claim this is garbage. This is just not what this means. Everybody see the problem? Okay, please. You got to keep in mind when I'm grading exams, I want to give you points, right? Please don't do this. It makes it hard for me to give points. Okay, so that in mind, that's nonsense. So what are we going to do? Here's the big reveal, right? I claimed that just recognizing that the partials of Zx and Zy are also functions of X and Y. Yeah, okay, no problem. Add it to the diagram. I'm literally just recognizing that Zx and Zy are also functions of X and Y, supplementing my diagram accordingly, right? And now with that done, there's no mystery. There's no mystery left at all. How am I going to interpret the partial, let's see here, the partial of Zx? Oh, there it is. With respect to R, oh, there it is. Nothing to it. We have two paths, thus going to give us two terms because there's two intermediate variables, X and Y. By the way, you can see those sort of working out. There's the X term from the X path. Here's the Y term from the Y path. And altogether, this partial is nothing more than that. So says the chain rule. And again, it's kind of like boring. It's like, well, yeah, here are these two things on the diagram. You look at the paths, you write down the terms. Boom, nothing to it. Yes?
If you were to have real numbers, how would you, like, just come up with ZX in a sense?
What, I don't understand the question, sorry.
Like, if this was done with actual, like, values, how would you get to ZX from...
So ZX is the partial of Z with respect to X. Right? So that it's just this alternative notation for partial of Z with respect to X.
But I thought you just said that you can't do that. You can't take the partial of Z with respect to X and then take the partial of Z with respect to R.
Not thought of as a single function. That's right. But ZX is a function of X and Y. So that's all. ZX being a function of X and Y being a function of R, it is perfectly reasonable to use the chain rule to talk about the sort of the composed partial.
So you would take it in terms of X first, and then you would take it in terms of R.
I'm sorry, I understand.
Like, let's say I had Z, I would take the derivative in terms of X, and then I would take it again in terms of R to figure out like an actual.
So what I'm showing you is how to do that, right? The way you're going to take the partial of ZX with respect to R, I mean, let's see, where did it go? That's what I'm interested in here. The way you're going to take the partial of ZX with respect to R is recognizing that it's a chain rule problem, right? And then using the chain rule to write it as things that you can actually crank out, right? So this directly, you can't just like use, shortcut rules, power rule, stuff like that, right? Because, ZX is not immediately a function of R. That would be nonsense. But this is, I'm now understanding it as a chain rule thing, and once you recognize it as a chain rule thing, the chain rule just jumps all over it, and everything in here is a direct computation. I saw a hand in the back. Oh, okay, yeah, cool. Okay, all right. So let's see here. By the way, same thing on the partial of Z with respect to partial of ZY with respect to R. There's ZY. There's R. And again, two paths, two terms, and this partial is the sum of those two terms. Again, just straight up using the chain rule. So ZY, it's some function of X and Y. The R partial of it, can't make sense out of it directly, but the chain rule just turns that into things that we can make sense out of. All right. How we doing? Okay. All right. And of course, look, don't forget, that you've got a constant here, for example. Constants come along for the ride, right? Nothing happened there. Likewise on the first one. And so there's a lot to keep track of. And make sure not to lose the things you're trying to keep track of. And then there's subsequent algebra to be done. For example, I know again how to take polar partials, right? And then don't forget that these two things, not immediately clear that those are the same. The y partial of zx, the x partial of zy, until you remember that for C2 functions, and at the top of this page indicated these are C2 functions. Mixed partials are the same. Okay. All right. And so, multiplying out, collecting terms, and here's your final answer. Okay. All right. Okay, so why would we ever care about such a thing? Or when is this going to come up? And I have what I think is a pretty great example. This is a very important object of study right here. It's called the Laplacian operator. It looks like sort of too simple to be useful. It turns out when you add the rectangular second partials, you get something that is extremely natural. And I know most of y'all are engineers. Y'all are going to be interested in various things, such as how do waves move, how does heat move, how do electrons behave. These are all pretty fundamental in physics. And it turns out that all of these a critical element of how to describe all of these very natural, very fundamental phenomena uses the Laplacian. Right, so this is a very important operator to write down. And the problem is, you'll notice the way I've written it down assumes that I'm playing in rectangular coordinates. We like rectangular coordinates. There's certain nice things about rectangular coordinates. But very often, certain scenarios are much easier to describe using spherical coordinates. I'm going to show you an example in just a few seconds. So here's the nice rephrase. This Laplacian, if you want to write it in terms of spherical coordinates instead of rectangular coordinates, that seemingly simple little expression in spherical coordinates turns into this. Now, a couple of things to say about it. First of all, why? Where did that come from? Right? And second of all, pass, right? I mean, which one of these would you rather work with? A lot of people are going to decide and go rectangular because, oh my gosh, look at the nightmares here. Right? Okay. Well, I'm going to try to change your mind on opposition to the spherical experience. This is actually way better, as it turns out. Now, again, example incoming. But let me talk about where it comes from first. Each one of these expressions, so for example, second partial with respect to theta, right, we're looking for a composition second partial, and you can just write it down using the chain rule, just like we did on the previous page. What we did on the previous page was two-dimensional polar coordinates. Right? This is three-dimensional with spherical coordinates. The equations are uglier. There's 3 of them instead of 2, and it gets weird and it gets tedious, and there's a lot to write down. But you can totally write what the theta second partial is, and you can totally write down all these other individual things, and then you can multiply and add them together and do what this formula says, and what you will get is exactly this. Just as an analogy, again, I don't want to write down all the algebra. The algebra gets way too ugly, but let's look at a polar analog. Same thing, same idea, but in polar coordinates. We've already written down how to write partials, an R partial in rectangular coordinates, right? So doing the composition, how do I, take a partial with respect to R? Well, that's this formula right here. Now, it doesn't look like we've seen that before, but we have. That is, in fact, a complete ripoff of this formula right here. Now, the difference is I didn't write down the function that we're applying it to. Right here, I gave a name to the function, whatever this thing is, that's a function of x and y, blah, blah, blah. Well, we're calling it z, so each one of these things looks like an expression that we know what to do with. I'm just making the observation here that you can think of this as an operator, d by dr, that's applying to z, and I'm just making the observation that this operator on the right, applied to z, does the same thing. And notice that's exactly what this is here. Said differently, if I were to just stick a z into here, there, and there, and there, this is literally exactly the equation on the previous page. Right? So this is old news, just written differently. Is that cool? Okay, so no big deal. And by the way, likewise, this is just a theta partial, written as operators instead of partial derivatives. Put a z on each one of those if you prefer, right? But it's the same thing. And then, if you want to compute something rectangular, here we have something rectangular. We want to figure out how to write it in terms of stuff in one of the curved coordinate systems. All right. Well, these rectangular things that you're interested in, solve for them. there's a little bit of work to be done there to solve for them. But you can solve for those rectangular derivatives in this system of equations, right? A little 2x2 system of equations. Y'all can do that. Good exercise, by the way. Make sure you can do that. Solve for those rectangular partial operators, and what you get is these formulas right here. What this tells you is if you need, for whatever reason, to do a bunch of rectangular partials, which, sometimes you do. Again, reminder, the Laplacian is rectangular partials. You need to do those rectangular partials, but if the function you're doing it to is already written in terms of polar coordinates, okay, fine. This is your shortcut. This says, fine, it's written in terms of polars. Great, let's take polar partials because they're easy, because the function's already in polar coordinates that you're dealing with. These are polar partials. Just look, you got to keep it honest, and you got to adjust accordingly and multiply by these, blah, blah, blah. And then, boom, there's your rectangular partials. It makes your life a lot simpler. Okay, so that's where the formula comes from. Again, at much, much more algebra in the spherical case. And I don't recommend that you wade through that. But if you're looking for a challenge, I guess you could. But anyway, let's see why we care. So here's, again, real stuff. Gravitational and electric potentials, right? I think y'all would believe it if I said this is important, right? Understanding how electric potential works. That's one of the main ways you understand electric fields, is by understanding the underlying potential function. And if you haven't had E&M yet, don't worry. Trust me, this stuff's important. But you'll see why and how in a physics class. So, turns out these potentials have to satisfy this equation. This is called Laplace's equation. And you'll recognize this is literally just the Laplacian operator. And what it says is whatever function you claim is going to be a gravitational or electric potential, the Laplacian of that function has got to equal to 0. Okay. All right. So here I have a candidate. Turns out this is right, by the way, for if you have a point mass or a point charge. But for the moment, I haven't shown that yet. I have not shown that this equation works. And right now, this is just a candidate. I think that this is going to work, but I have to actually show that it does. So I'm going to have to take this function, take its Laplacian, and confirm that I get 0. And that's a potentially nasty calculation. So let's do it, or let's at least, try to anticipate how hard this is going to be. There's my Laplacian. My function f here is there. And my very first attempt to compute del f, right, is going to be this right here. And, oh my gosh. By the way, it's a healthy exercise. Everyone should do this once in their lives. I did mine. It's your turn. Enjoy. Right? It is tedious. It's doable, but it's all else being equal, it is significant. You can kind of see it coming when you start taking derivatives. You've got a square root in the denominator, and then but with a chain rule, right? Because it's a square root of a function of x, y, and z, right? And then you take a second partial, then you're going to have a product rule come up, and oh my god, it gets a little out of hand. It's doable, right? Stay organized, write neatly, right? Be deliberately careful about how you write your expressions, and it'll only take you a page or two of calculation. So let's call that plan B. All else being equal, I'd prefer not. Here's my alternative. My alternative is to take my Laplacian, apply it to my function, this time using spherical coordinates. Now again, same function. This is the same function. It's the exact same thing, just written in terms of spherical coordinates. This is the exact same operator. Again, just writing it in terms of spherical coordinates. And again, we've already kind of decided we were not optimistic about this. This looks like a nightmare. Look at all the monstrosities. Okay. But let's do it. And look how easy this is going to be. This could be totally awesome. This function, the very first thing I need to do to it is compute the partial with respect to theta. What do I get when I take a partial with respect to theta of a function that doesn't have any thetas in it? 0. Poof. And then everything else in this term is something I'm doing to 0. And so this entire term disappears in a puff of smoke. Yeah? Isn't that nice? Right? Really, really nice. Okay, all right. But we got lucky on that one. Okay, let's look at the second one. Okay, all right. So that one looks even weirder. But wait a second. Again, the very first thing that I have to do is take a phi partial of an expression that doesn't have any phis in it. And so again, this too, immediately 0. Snap. Puff of smoke and all that. All right, y'all coming around? Starting to see how this, all of a sudden, this gigantic nightmare of a monstrosity, all of a sudden is not looking so bad, right? Pretty nice. Okay, now those are gone, but we do then have to consider this last term, depending on how you look at it. Very first thing I have to do is take a rho partial. This does have a rho in it. So I can't just, just celebrate the immediacy. I'm going to have to actually do one. So I'm going to get negative k over rho squared, right? I'm going to take negative k over rho squared. I'm going to multiply by rho squared. That makes this product right here a constant. Right? The rho partial was negative k over rho squared. Multiplying by rho squared, I get negative k. I get a constant. And then again, I think I heard somebody say it already. You take any sort of a partial of a constant, you get 0. And again, then this entire thing wrong color. This entire thing goes away. And again, all I needed to do was show that this is 0. And we're done, right? No square roots, no fractional exponents, no quotient rule, product rule, right? It just, poof, just happened. Is that cool? Okay. What happened here? Why in the world would spherical coordinates have been so much nicer in a situation like this? And the answer ultimately is right here, in my opinion. The point is, it just makes sense to think of a function like this that clearly only depends on distance from the origin in terms of a coordinate system where distance to the origin is one of your variables. It's just natural, right? It just makes sense. And especially once you've done a calculation, as y'all have now, right? Y'all walk through this calculation. Once you've done one of these, keep your eyes open, right, for situations where what matters only depends on distance from a single point, which you are free to call the origin. And by the way, there's a lot of such scenarios, right? So another area where you score big on this sort of a strategy is if you do quantum mechanics. And for example, if you want to understand, all the y'all probably remember from high school chemistry class, they talk about the orbitals, right, of electrons in a hydrogen atom. Y'all seen that before? And they talk about how, there are 2 that can be in the bottom orbital, and then there are, I forget, is it 8 in the next one? Is that right? And then et cetera beyond that. Well, why is that? And I got told in high school a bunch of nonsense lies about how, they just won't fit. And that's not what it is. It's actually very simple. You can write down Schrodinger's equation for the hydrogen atom, the thing that matters is potential, electric potential. Electric potential depends only on distance to the nucleus, only on distance to what we're going to call the origin. It puts you in a situation that's very much like this. Right? And so when you solve Schrodinger's equation, oh my God, don't do it in rectangular coordinates. What are you, like, you're just looking to make your life difficult? No. Do it in spherical coordinates. This is way easier. And it's not quite this easy, but it's way easier, and you can actually write down, there's a finite number of solutions. There's just only so many solutions to that PDE. And those solutions, those finite number of solutions, are what they call orbitals. That's why, and it's not about electrons fitting, right? It's about how equations get solved. And again, this something morally equivalent to this is why it works so well. Okay. All right, moving along. So that finishes 2.5. We're going on to 2.6. I'm going to start off with just kind of a reminder about partial derivatives, and there's a lot we can do with partial derivatives, right? So for a appropriately differentiable function, a partial derivative, you can think of it as a slope. You can think of it as a multiplicative factor. These are our kind of primary interpretations, I guess. Different points of view. But anyway, here's a couple of other facts. Now, we haven't written these down before, but these are easily confirmed. An alternative way to think about the partial derivative is that it's what you get if you're at, whatever point where you're evaluating the partial. If you just start moving, literally, this little parameterization here just has you start moving in the EI direction. And that's what a XI partial means. And then you keep track of how fast is the function changing when you're at that point and moving in that direction. This is just literally writing down the equation, as a algebraic expression, what we mean when we talk about what a partial derivative is. Now, if you want to confirm this, you can view this as a chain rule problem. F is a function of x, y, and z, and this parameterization on the inside is literally giving you x, y, and z as functions of t. And use the chain rule, write down what the chain rule says, and what you'll find is that you literally get this partial derivative as your answer. And it's a nice little exercise. I encourage everybody to give it a try. And then another thing we've never really written down is that the partial derivative can be thought of as this dot product, which seems unnecessary to write down. But if you have the vector including all of the partials, and then you dot it with a vector that's mostly zeros, right, with a 1 in a single position. Well, when you do the dot product, everything gets multiplied by 0 except one partial that gets multiplied by the one that's in this vector, and you get this partial. So easier calculation, but another good one to make sure that you can do, so I encourage you to do that as well. Okay, all right. Everything we've got on the screen here applies to partial derivatives. Notice everything we have on the screen here is described in terms of a standard basis vector. Right? In other words, I can make sense out of partial derivatives. Everything we know about partial derivatives we can make sense of by talking about how they come from standard basis vectors. And here's where things get a little subtle, a little bit sort of weird. What is a standard basis vector again? Y'all remember what a standard basis vector is? It's where you write the coordinates in the mostly zeros with a 1 in a single position. Okay, but wait a second. So what a standard basis vector is defined in terms of coordinates. Coordinates are made up. They're arbitrary. We pull them out of a hat. They're not intrinsic to the world. Right? So, Here's my favorite sort of argument. The lines, those kind of wavy lines that I've got drawn here, by the way, this is the same picture, just drawn twice. This is supposed to be contour lines on some hill somewhere, right? And you're on a hike, and these are the contour lines. And V and W here represent a couple of different directions you might want to hike. And notice how I haven't said anything about coordinates. That mountain exists, independent of coordinates. Now, you might like to always write location in terms of, east-west and north-south. And that's, there's a lot of precedent. And we do that because of blah, blah, blah. But it's made up. You don't have to do that, right? You are perfectly welcome to set up any coordinate system you like. Doesn't matter. So I'm going to repeat for rhetorical purposes, what's a standard basis vector? And it's tempting. You look over here on the left where I've got my coordinates set up in what you might call the usual way, where maybe this is east-west and that's north-south. And so it would appear that, and by the way, these are unit vectors, would appear that V is a standard basis vector and W is not. But that's arbitrary, made up. I mean, it's just because I made this weird decision to decide to use north, south, east, west. I am perfectly within my rights to say, phooey on that. I want to keep track of location with these coordinates. It's just as mathematically valid. And now W is a standard basis vector. V is not. Right? Is that cool? Is everybody with me? So what's the upshot? I mean, why does this matter? I mean, technically we recognize that the mountain existed before the coordinates. Altitude existed before the coordinates. But we do need coordinates to get stuff done, right? But very importantly, coordinates are a arbitrary choice that comes later. So the point here is that everything that I've got written down up here, I mean, I called it about partial derivatives, but let's kind of ignore that. These things that I've got written in purple here, that slope of the graph, that multiplicative factor, this expression, that expression, these things are always going to be equal. This and this and this and this are always going to be equal for any vector which I can claim to be a standard basis vector, which is all unit vectors. All unit vectors could be, just set up your coordinate system appropriately. Any unit vector could be made to be a standard basis vector. So these will always be equal for any unit vector. You buy it? It's a subtle point, right? So look, we are trained from a young age to think of coordinates as absolutes, and that's how you do. These are the things, and it almost feels, in some sense, looking back on how you've done math in the past, that coordinates are what you are studying, and they're not. Coordinates are a tool to help you study what you want to be studying. You're not studying longitude and latitude. You're studying the mountain. Everybody see what I'm talking about? Okay. All right. So anyway, the punchline is, I can write down this definition. I can write down, and I'm going to use the term, by the way, directional derivative. I can't say partial derivative because I don't want to be confined by coordinates, right? But I'm just going to say, the common term is directional derivative of a function f in the direction of a unit vector v. And I'm going to define it to be, this thing that we just got through talking about, that expression, which is equal to that expression, which is a slope, which is a factor, right? So these things that are all equal to each other, we're just going to give them a name, directional derivative. This is the notation we're going to use. This is a particularly convenient computational formula. I like this as a nice sort of intuition for how to think about it. Excuse me. And the interpretations I get of directional derivative are, well, it's the slope of the graph in that direction. And it's the multiplicative factor as you move in that direction. And one last little notation, then we'll call it a day. Thinking about this interpretation right here, that it's the factor. In particular, it's what you multiply by input changes, discrete changes or rates of change, whatever, right? To get output changes. Well, again, could be discrete, could be instantaneous. And what do you think would be a really good notation for, what's going to go? What do I multiply by ds to get df? Or what do I multiply by ds dt to get df dt? I think it's pretty persuasive that the factor would be pretty naturally denoted by df ds. Doesn't that seem like a reasonable? I mean, my gosh, what else would you want to call it? I mean, it's very reasonable. And it's also very kind of explicitly telling you what it is. I want to know how much the function changes per unit distance that I move in whatever direction we've decided on. So df/ds, very, very natural. Okay, so that's what a directional derivative is. We're out of time. We will pick up next time with some examples. And see y'all later. Have a good rest of your Monday.